So this is the first lesson of calculus. We're not going to do any calculus today, but hopefully what we do today is going to show you the need for calculus. So we're going to talk about the concept of an instantaneous rate of change. So the question is, can change occur at an instant? As students of life and algebra, you have studied many rates of change for different situations. How fast we drive, how our savings grow over time, the rate that the world population changes, our growth rate every year, unemployment rates, and so much more. In each of these studies, we can express one variable in terms of the other as a function. So y equals f of x. When we talk about rate of change, when we're talking about a linear function, we're talking about slope. So we're going to pick one of these concepts, which is velocity. And we're going to talk about the average velocity versus an instantaneous velocity. So consider an object that travels in a straight line. And the average velocity over some given time interval can be defined as the ratio of the change in position or displacement or net change to the elapsed time period. Okay, so a ratio is... There we go. A ratio is just a fraction. And it's the change in position. So change in position over the change in time. And then we're going to shorten that delta D over delta T, and that's the change in the distance over the change in time. So this is your ratio, but this ratio means slope. Okay, so that's how you can find the average velocity over the course of 5 minutes or 2 seconds or an hour. However, when we think of velocity, we usually mean instantaneous velocity. Now, make sure you know the difference. There's a difference between velocity and speed. Velocity is more about your acceleration. So instantaneous velocity, which indicates the speed and direction of some object at a particular moment, which could be faster or slower than the average velocity. Can you explain why we can't define instantaneous velocity as this ratio? So think about it. Instantaneous velocity would be delta D over delta T. So what would go wrong in trying to figure that out for something that occurs at an instant? And the problem is that your delta T would be 0 because it's at a split second. It's not over the course of time. Even if that time is microscopically small, it's still at one specific instant. So your delta T is 0, and you know that we can't divide by 0. So this is kind of where all the tools in your tool belt fall short of finding instantaneous velocity, and this is where calculus is going to pick up. So for right now, we're just going to estimate an instantaneous velocity. To do that, I know my delta T can't be 0, but I want my delta T to be very small, so I can get as close to 0 as possible. Now, not just as close to 0, but we're going to generalize this big idea with this principle. So the average velocity over a very small time interval is very close to instantaneous velocity. Not exactly, but it's a good approximation. So here's a good example. It says if you climb to the top of the Tower of Pisa and drop a coin to the ground, estimate the instantaneous velocity. Again, we have to estimate it because we don't have the tools to find it exactly. At 0.7 seconds. Use Galileo's formula, the S of t, and that's your position, is 16t squared to compute the average velocity in feet per second over the time intervals listed in the table below. Okay, so first of all, let's look at our time intervals. So I'm going from 0.7 seconds at the beginning of each of these intervals, but this one's going to 0.71. This one's going to 0.705. So you can see that these values are getting closer and closer and closer to 0.7, which means those intervals are getting smaller and smaller and smaller. So what we're going to do is we're going to look at the values of our average velocity and see what velocity it's approaching. So some of this should start to trigger some stuff that we did at the end of calculus. Okay, so I'm going to be finding the slope because that's what average velocity is. So I'm going to take my calculator and I'm going to go to my y equals and I'm going to type in 16x squared. And I'm going to go to my table, but I need to set up my table setup first. So I'm going to start at 0.7 and I want to go up by 100th. So now I'm going to my table. So you can see there's the 0.7 and there's the 0.71 and these are the y values. So these are the distances. So I'm going to do, just like slope, I'm going to do y minus y. So those two values minus each other. And then on the bottom, I'm going to do x minus x. And just whichever one you pick first, make sure you pick the same one first for the x's for the bottom. So I'm not going to actually write that out. I am going to just tell you that the result is 22.56. Okay, so now I want to find it on this interval. So I need to go back to my table set. I'm going to start at 0.7 and I want to go up by 0.005. So now I have my 0.7 and I have my 0.705 and I have the two y values that go with it. So I would do y minus y over x minus x, and that is going to give me 22.4016. And again, I'm chopping decimals, so we just want to make sure that when we write a conclusion, we're using the word approximately or about. Okay, so I'm going to do the same thing for the next one. I'm going to change my delta, my table, the change to 0.0001. I'm going to do y minus y over x minus x. And I'm going to get, oh, shoot. Okay, sorry. This one, if y'all can change that for me, this one was 22.48. So sorry. This one is 22.4016. Okay. Then the next one, in changing my table and doing y minus y over x minus x, I get my slope to be 22.4008. And this one's 22.40016. Now notice I'm going forward with my decimals because I'm really trying to see what this is approaching. Again, this should make you start to think about things that we talked about in pre-cal. So what I can see is as these intervals are getting smaller and smaller and smaller, and also not just smaller, but as they are getting really close to honing in on time equals 0.7 seconds, I can see that the average velocity is approaching, I'm going to say 22.4 feet per second. So in my conclusion, I can't just write 22.4 because I have to state what it is that I found, what does it mean, and what are the units of measurements. So I'm going to put it in terms of this problem. So we have a coin. So the coin is falling. And then here's a keyword, at a rate of about, that's a keyword, 22.4 feet per second. And unfortunately, a lot of people will stop there. But this coin isn't falling at a rate of 22.4 feet per second for the whole time that it's falling. We only found this approximation of an instantaneous rate of change for 0.7 seconds. So I have to state that. So the coin is falling at a rate of about 22.4 feet per second at t equals 0.07, nope, 0.7 seconds. So just be careful about your conclusion. Okay. So the study of the rate of change is fundamental to the study of calculus. It's kind of the foundation of calculus. In our first example, we allowed the time interval to shrink to 0. And again, that should make you think of something. So we can say that the average velocity converges to the instantaneous velocity, or that the instantaneous velocity is the limit, there it is the limit of the average velocity. Okay, now I'm going to show you an abbreviation for instantaneous velocity and for average velocity, and they're coming up in the notes. But the instantaneous rate of change, IROC, equals, or let's do this, let's do approximately, the limit as, okay, now we want the limit of the time, the change in the time to go to 0. I don't want my time to go to 0. I want the change, the time lapse, to get as close to 0 as humanly possible. And I'm taking the limit of the average rate of change, or the AROC. So the IROC is approximately the limit as delta t equals 0, or approaches 0, of the AROC. So let's talk about a graphical representation of both of these, and then we'll talk about analytical. So average speed, which is AROC, is defined as the total distance traveled divided by the elapsed time period. So, and we did that, delta D over delta T. Okay, and you can find that, we just did that in the chart 5 different times. Graphically, the average speed is the slope of the secant line. A secant line is just a line that goes through 2 designated points on the graph. So this is the secant line. So the slope, the AROC, is the slope of the secant line, which in this case, and I'm just going to do rise over run, so up 1, 2, 3, over 3. So his slope is 1/3, roughly. And that's his AROC. That's his average rate of change. Okay, so I can see it graphically, slope of the line, and then I can do it analytically, just rise over run, or y minus y over x minus x. Okay, so now let's talk about instantaneous rate of change, or IROC. It's the speed at a specific instance in time. So where t equals t sub 0 is the limit of the average rates of change. Okay, that's a little up there. So let's look graphically. Graphically, the instantaneous speed is the slope of the tangent line at a specific point. Well, a tangent line is a line, a straight line, a linear line that touches a curve at one spot. So if I were to estimate it, I'm going to say it's like that. The whole first part of calculus is finding the slope of that line, or the equation of that line, and then applying it. So this is the first 4 chapters of calculus right here. Now I can sketch the tangent line, which I did, and I can estimate the slope of this line, the instantaneous velocity. But your line may not look just like mine. We're eyeballing it. So let's see. If I did a point here and, I don't know, a point there. 1, 2, 3, 1, 2, 3, 4. So I'm going to say the IROC, which is the slope of the tangent line, is about 3/4. So graphically, I can see it, although I probably didn't draw it perfect. Analytically, I can't find it. I can find this guy because this line was exact. This line is not. That was an estimate. Calculus is going to help us find it exactly. Okay? So example 2, spin class heart rate and exercise. Have you ever taken a spin class at the gym? Then you know that after the class is over, your rapid heart rate decreases as time passes. Let h of t represent your heart rate. Write an expression for the rate of change of your heart rate over the period from t equals 0 seconds to t equals 90 seconds after you have stopped exercising. Now, I want you to focus on this part right here. You can't skim over words like that because that is letting you know, write an expression. That part is letting you know that you're not going to be able to find an answer exactly. You're just writing an expression that would represent that solution. You don't have enough information to find the average rate of change of your heart rate for the first 90 seconds after you exercise. So, what we are trying to find is the average rate of change. So it's going to be the change in your heart rate over the change of time. Well, the change of time is easy, and I'm going to do 90 minus 0 instead of 0 minus 90 just to stay positive. So 90 minus 0 is my time. Now the problem is I don't have enough information to find what my heart rate is. But if I was going to find it, I would take the 90 seconds and I would plug it into my function and get my heart rate. And then I would take 0 and plug it into my function and get my heart rate. But I don't have an actual function. I don't have what h of t is defined as. So I'm just going to show that I would do h of 90 minus h of 0 if I could. So then the only thing you can do to clean this up is on the bottom. 90 minus 0 is 90. So there you go. There is an expression that represents the rate of change of your heart rate over the period from 90 seconds, or from 0 seconds to 90 seconds after you have stopped exercising. So again, this was a rock. Okay, last example. We're going to talk about a roller coaster. A hypercoaster is a special circuit roller coaster with a height measuring greater than 200 feet. If a new hypercoaster is under design to have its largest drop on the circuit modeled by the equation below, where d of t is measured in feet and time is measured in seconds. So this function represents the drop in feet of this hypercoaster. So I want to find the average speed from 2 to 8 seconds. I want to find the average speed from 4 to 6 seconds. Now, honestly, those are both things my Math 1 kids could do. They know that average speed means average rate of change, and they know that means slope. Part C says estimate the instantaneous speed at exactly 5 seconds, and they were very nice and gave me the intervals. Now let's focus on something. Part A is going from 2 to 8 seconds, and Part B is going from 4 to 6 seconds, and then I want exactly 5 seconds. So you can see that it's kind of honing in on 5 seconds, and then these time intervals are really getting close to those 5 seconds. So the AROC is going to be d of 8 minus d of 2 over 8 minus 2. To get what d of 8 is, I'm going to type this into my calculator, and then I'm going to go to my table, and I'm going to scroll down to where 8 is and where 2 is and get those values. I'm not going to show you how to do that because I assume that you know. So we're going to, I'm just going to tell you what those values are. So 671.36 is your d of 8, and 290.54 is your d of 2, and then 8 minus 2 is 6, and that's going to give you approximately 63.47, approximately because we are chopping off some decimals. So I can say that the average rate of change of hypercoaster is about 63.47 feet per second, but not the whole time, just on this interval. Or you could say from 2 to 8 inclusive seconds. Okay, so now we're going to do it again, and we're going to find it from 4 to 6 seconds. So the AROC is going to be D of 6 minus D of 4 over 6 minus 4. And again, I've got that function in my y equals. I'm going to go to my table. D of 6 is 470.18. D of 4 is 373.16 over 2, and that's going to give me approximately 48.51. So I can say that the AROC of hypercoaster is about 48.51 feet per second from 4 to 6, seconds. Okay. So let's see, we went from 63.47 feet per second. We're down to 48.51 feet per second. Okay, so now I'm going to leave that function in my y equals. I'm going to go to my table. I'm going to start at 5. I'm going to change my delta table to 0.1. And I'm going to do y minus y over x minus x. And I'm going to get 47.3997. Now, I'm not working this out because I hope that you understand how to find slope, and you're going to practice this on your homework. Then I'm going to change my delta table to 0.01, and again I'm going to do y minus y over x minus x, and I'm going to get 46.7142, and for this one 46.6474. Now this one seems to be a little less obvious as to what we are approaching. So I'm just going to go with this bottom number. Like, it's not approaching 46 even. I mean, we're already 3 decimals away, and we're at 46.6474. I'm not even going to say it's approaching 46.6. I don't know how far it's going to go. So I'm going to stop with that answer right there. So I'm going to say the IROC, instantaneous speed, at 5 seconds, because again, this is IROC, so this is at one particular time. So the IROC at 5 seconds is, now here's the big word, about, because remember we are estimating, is about 46.6474 feet per second. And that's kind of what we were supposed to do for D. There it is. Okay, so I hope this helps you understand the difference between AROC, average rate of change, which is slope, and IROC, which is instantaneous rate of change, which you can't use slope because you can't divide by 0, but that you can use a limit of the AROC to approximate the IROC.